It's my pleasure that Professor Chalomilau has accepted to be the chair for this session. So I hand over to him.
And it's my pleasure to host this session. So we'll wait 3-4 minutes before starting so that people can join us. The slides are already visible, so everything seems to be in order.
Yes.
Yeah, on the website research seminar, it's incredible. There's an inflation of talks per day. It's just amazing.
That's right. I mean, the guy at MIT, Andrew, gosh, I forget his name, who set that up, did a really fantastic job. And basically everyone who's having a seminar or a conference posted on researchseminars.org. And it's very well constructed. My proof is that even I can manage to upload seminar talks. And usually I'm pretty bad at that sort of thing. But when I have my number theory seminar on the New York seminar, I can upload the speakers, the abstracts, whatever, and it's very, very easy to do.
Yeah.
But the number, I mean, it's like archive. The number of contributions goes up exponentially.
Yeah, it's amazing. I had a look yesterday. It's just amazing. Yeah. So people are slowly joining. We'll wait 2 more minutes. Are you ready to start, Mel?
Yeah.
Okay, so I think we will start. So it's a great pleasure to welcome everybody to the third session of today. And it's a great pleasure to have Mel Nathanson, who needs no introduction, from City University of New York, who will give the first talk of the third session, and he will speak about Sidon sets for linear forms. Mel, it's all yours.
Well, thank you very much, and I thank the organizers for the opportunity to speak. Sidon sets have been mentioned already in this meeting. The idea here is simply that many of the concepts and constructions in additive number theory extend in a natural way to linear forms. So the central object in additive number theory is the h-fold sum of a set of integers. So you have a set A of integers, and you look at all the numbers that can be written as a sum of h elements of the set A, not necessarily distinct. And as is usual, you say that A is a basis of order H for some set S if every element of S has a representation as a sum of H elements of A. The terminology is somewhat curious, but we say that A is an asymptotic basis for S if with only a finite number of exceptions, every element of S is a H-fold sum of A. And let's say A is a basis of order H for almost all S. If the set of elements of S that are not sums of H elements of A has relative density 0 in the set S. And a sit-on set, well, we say A is a sit-on set, or sometimes called a BH set, if every element in the sum set has an essentially unique representation as a sum. So I want to consider a linear form. So a linear form, let's say with integer coefficients, is just this expression C1x1, C2x2 plus up to CHx sub h. If you take a set of integers and an integer c, the dilation is just what you get by multiplying every element of A by the number C, and A to the H is just the set of all H tuples of elements of H. So you have this linear form phi, and phi of A is just the image of A under this set. So you evaluate phi at all the H tuples in A. This is exactly what it is. You can also express this as a sum of dilates, and using the language of sum of dilates, there's a very large literature on the size of such sets. If you take the simplest linear form, which is just all the coefficients equal to 1, x1 up to x sub h, then the image under this phi is just the h-fold sum set. And we have the representation function associated with the form. So you have a form phi, you have a set A, and you have a number n, and the number of representations is just this number of ordered H tuples of elements of A, where phi of A1 up to AH is equal to n. And we say that a set A is a phi basis for almost all the integers if almost every number has a representation of this sort. So equivalently, the representation function of a basis for almost all integers is some integer valued function or non-negative integer valued function of plus infinity, where f inverse of 0 is density 0. And one could, for example, ask the inverse problem, for what such functions is there actually a set A whose representation function is the function f? So this is really just sort of background to give some example of results that have used binary linear forms. So here's a theorem. If you have a binary linear form, C1x1 plus C2x2, where the coefficients are non-zero, relatively prime integers, C1 times C2 is plus or minus 1 or minus 2. If you take any function on the integers to non-negative integers together with infinity, where f inverse of 0 is asymptotic density 0, then there's always a set of A of integers whose representation function is exactly this function f. And if you take the special case where f is identically equal to 1, this says that there's what is called a unique representation basis with respect to this form. So given this form C1x1 plus C2x2, satisfying these two conditions on the integer coefficients, there's always a set A such that phi of A represents every integer uniquely. And I noticed I was looking for some results that involve linear forms, and this was an old result. And I thought it was appropriate to mention it because it was published in a paper in 2007 that appeared in a volume dedicated to Jean-Marc on his 60th birthday. So birthday papers are sometimes nice. Here is another old result about linear forms. If you take the linear form x plus 2y, so we're looking at the set A plus 2 times A. If you have a set A of k integers, there's a lower bound for the cardinality of this, which is 3k minus 2. And for any integer c at least 3, you have a lower bound of 7/2 k minus some big O of 1. And this was very nicely extended by Boris Buch, who proved that if you have a set of k integers, a plus 3k always has at least 4k, basically, elements. And if you take an h-fold linear sum, take this linear form where the GCD, well, the GCD of the coefficients is 1, but that the size of the set A evaluated at this linear form is at least this constant times k minus some little o of k. So these are just some examples of the use of linear forms in additive number theory. But what I want to talk about are sit-on sets for linear forms. So we don't have to take integer valued forms. You can take any field and consider linear forms where the coefficients are scalars in the field. Take any vector space over the field. I mean, it could be elements, it could be the field, but vectors doesn't matter. And you look at the set of all H tuples of elements of this subset A of the vector space. And we're interested in the image of A under phi. So you just evaluate phi at all the H tuples that come from the set A. And we say that a non-empty subset of our vector space is a sit-on set for the form if it has the following property. If you have two H tuples and phi of A1 up to AH equals phi of A1 prime up to AH prime, then the two H tuples are the same. So another way of saying that simply is that you have a sit-on set for the form phi as simply a set A of vectors where phi is injective is 1-to-1 on the set of H tuples. Every number has a unique representation. Every number that's represented has a unique representation in exactly this form. So to state the obvious fact, if you have a set with just one element, it's a sit-on set because there's only one H tuple, so there's nothing else you can do. So it's only interesting to look at sit-on sets that have two or more elements. And so if you're given a form, you can ask whether a sit-on set exists. And there's a simple obstruction to the existence of a sit-on set with respect to a form. So we have our form, summation Cixi. If you take a subset I of the integers from 1 to h, the subset sum is just the sum of the coefficients C sub I for I in this set I. And if I is empty, this is just 0. So suppose we have disjoint subsets I1 and I2 of our index set 1 to h, where they're not both empty. One can be empty, but they're not both empty. And the sum of the coefficients SI1 equals the sum of the coefficients SI2. So we've partitioned the index set from 1 to h into 3 sets, I1, I2, and I3 is everything else. So suppose we have this form, this linear form phi, where you have two disjoint subset sums that are equal. And take any set A of vectors with at least two elements and at least two vectors. It's not a one element set. So you can choose vectors u, v, and w, where u is different from v. W can be equal to u or v or not, doesn't matter. And I define two H tuples. So AI is u for I and I1, v for I and I2, and w otherwise. And A1 prime switches the AI prime switches the u and the v. AI prime is v for I and I1 and u for I and I2. So we have two distinct H tuples. And you do the calculation, phi of A1 up to AH. So you have the sum over the I1 terms, the sum over the I2 terms, the sum over the I3 terms. But for I and I1, the AIs are all equal to u, and for I and I2, the AIs are all equal to v. For I and I3, the AIs are all equal to w. So we have this expression. But of course, this subset sum equals this subset sum, so we can interchange these two. And we turn it, and we get exactly this sum where with the AI primes replacing the AI. So phi of A1 up to AH is phi of A1 prime up to AH prime. So A cannot be a phi Sidon set. So if you have this condition of two disjoint subsets coefficient subs being the same, no Sidon set can exist. So we have this sort of negative property. We say that a form has this property n if there are no disjoint sets I1 and I2 with the same subset sums. And you just notice that if a form has this property, then it follows that all the coefficients are non-zero. So an example of a form that has this property is just the form where you take as your coefficients the powers of 2. So a sum of powers of 2 equals another sum of powers of 2 if and only if the summands are the same. So no coefficient sum here equals another coefficient sum. So this is an example of a form that has the property. And if you look at our favorite form, just the sum of the x's, this doesn't have property n. So so you have to be very careful about this point. For this linear form, there is no Sidon set. But that's only because we consider order in our definition of a Sidon set for a linear form. Now, this obstruction to the existence of a Sidon set turns out to be the only obstruction. And to prove that, I use this simple notion of a contraction of a linear form. So you take a linear form, and for every subset of the this index set 1 to h, every subset j, you let phi j just be the sum of cj xj, but just for the j's in the set capital J. So we're just looking at like a partial sum of the form. I mean, if J is the empty set, this is 0, and if J is 1 through H, this is just the original form. So we call this a contraction of the form phi. And if you take any vector space over the field and any subset A of vectors, then phi j of A is just the image of A under this contracted form phi sub j. And you can observe that if A itself is a phi Sidon set, then for every j, phi j is a Sidon set for every non-empty subset. So we have our linear form phi. We take a set J of indices. JC is the complement of J. If you take any set of vectors A and any vector B that's not an A, you can look at phi J of A and translate it by this. This is B times the scalar. This is the sum of the coefficients that aren't in the set J. So phi J of AB means the image of phi j under A translated by this vector. And there are sort of two technical lemmas that I need. I never find these technical things elucidating in a talk, but so you'd have this linear form phi with coefficients in F. You have a vector space over F and a subset A of the vector space, and a vector B that's not an A. So this is saying what happens to the image of A under phi if you add a vector to A. So phi of A union B is exactly the sum of these phi j of ABs. So if A union B, so this is just a fact, right? So you look at, you evaluate phi at A union B, and you just look at the places where B occurs as a value of a variable, and you get a union of disjoint sets. And so this set is the union of all these guys. And if A union B is a phi sit-on set, then these sets phi j of AB are pairwise disjoint. And conversely, if A is a phi sit-on set, and if if you take a B not an A, and phi j of A comma B are these sets are pairwise disjoint, then A union B is a phi sit-on set. So this is sort of a criterion of when, if you start with a sit-on set, you can find another element added to it and still have a sit-on set. We also have now the following little lemma. So you have, again, your linear form, phi, a vector space over the field F, a subset, infinite subset of V, and take a finite subset of X. So if the linear form phi has this property n, that means no subset sum of coefficients equals another subset sum of coefficients, then there's always a B in X such that these sets phi j of B comma B, that means you can take B, add an element B to it, and these sets are pairwise disjoint. And the point of this is to be able to make the following statement. So this is, I guess, theorem one, that F be a field, let V be an infinite vector space over F, let X be an infinite subset of V, and you take a linear form with non-zero coefficients. So the following three statements are equivalent. The first is that this infinite subset X contains an infinite subset, which is a phi sit-on set. Okay. The second statement is, well, the set X contains a phi sit-on set with at least two elements. Well, of course, one implies two, because if there's an infinite set, there's a set that has at least two elements. The third property is that the form phi has this property n. The coefficient subset sums aren't equal. Well, we already proved that. So we proved that if a form doesn't have property n, then there's no sit-on set with two elements. So if a sit-on set has, so if there's a sit-on set with at least two elements, the form has property n. And the lemmas that I just posted and flew by show that if the form has this property n, then in fact there's an infinite sit-on set for the form. So this obstruction to a linear form having a sit-on set is necessary and sufficient. It's the only obstruction to the existence of a sit-on set. Okay. All right, now I want to show that in a certain sense, if you have a sit-on set, you have a lot of them. So I want to talk about perturbations. So we have a field F that has an absolute value. So it's just some non-negative real valued function, which is zero precisely when C is zero. It's multiplicative and it satisfies a triangle inequality. There's always a trivial absolute value, which is 1 for every non-zero C and 0 at C. If the absolute value is non-trivial, then it certainly is the case that the field is infinite. And if you look at the inf of the absolute value of C for all non-zero C, the inf is 0. So we have a field that with an absolute value, and you take a vector space over F, and a norm on the vector space with respect to the absolute value is again some non-negative real valued function, which is 0 only for the vector 0. It is homogeneous with respect to the field. You know, the norm of scalar times the vector is the absolute value of the scalar times the vector, and the triangle inequality is satisfied. So there's the following lemma. You have a field with a non-trivial absolute value, a normed vector space over the field. Take any finite subset of the vector space and let B be a vector in the vector space. You have this linear form phi with coefficients in F. So if this form has property n, again, this property that the coefficient subset sums of the form are distinct, then for every epsilon greater than 0, there's a non-zero vector A, such that with respect to the norm, A is within epsilon of B. And for every subset of the index set 1 through H, these contractions, phi sub j of A prime A, are pairwise disjoint. And remember, there's a connection between these sets being pairwise disjoint and having something like a Sidon set. So let's see, let me just define what is a perturbation of a sequence. Again, you have a field with a non-trivial absolute value, a vector space V that has a norm with respect to the absolute value and the positive integers. And you have two sequences of vectors, not necessarily distinct. And you let epsilon sub k, epsilon is the sequence of positive real numbers. So we say that the sequence A is an epsilon perturbation of the sequence B if the norm of AK minus BK is strictly less than epsilon k for all k. So you have this sequence B, and you have this sequence of little epsilons, and a perturbation of the sequence B is a sequence A where AK minus BK, the norm is less than epsilon k for all k. So now we have the following theorem. You have a field with a non-trivial absolute value and a vector space over the field, a norm with respect to the absolute value, and the sequence epsilon of little positive real numbers, and a linear form phi with this property n. So any sequence of vectors that you pick, B sub k, there is always a phi Sidon set A of vectors such that AK minus BK is less than epsilon k. So this says something about the ubiquity of Sidon sets, that you take any sequence whatsoever, and you can find this tiny, 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 tiny little perturbation of B that gives you a Sidon set. Right, so AK minus BK is less than epsilon k for all k. The BK, you can choose them in any stupid way you like, but no matter how badly you choose the BK, there's always some tiny perturbation that gives you a Sidon set. And in particular, if you take your epsilon k's going to 0, this says that for any sequence of vectors BK, there is always a phi Sidon set A sub k where AK is minus BK goes to 0. So AK is asymptotically equal to B sub k. Now, the absolute values we love, besides the usual absolute value, are the p-adic absolute values. So that this be the usual p-adic absolute value normalized so that the p-adic value of p is 1 over p. So we have the following statement. So now let's take, so I'm going to be looking at rational numbers and integers. So phi is a linear form with rational coefficients that has this property n. So that means that with respect to this form, there do exist infinite Sidon sets. Take a finite set of primes. Doesn't have to be just one prime. It can be a large set, but finite. Take any finite set of integers and take any integer b. Then for every epsilon greater than 0, there are infinitely many positive integers a. So a minus b p-adically is less than epsilon for every prime in the set p naught. So a is p-adically close to b for this large finite set of prime numbers. And if I look at this phi sub j of a prime a, so this is the truncation of, or the restriction, or the contraction of the form phi by the set j, translated by this number. These sets are pairwise disjoint. Right. So I can find an A close to B, p-adically close to B, such that I have this family of pairwise disjoint sets. And I can now give the following theorem. So that A be any linear form with rational coefficients that has this property n, this property that the subset sums of the coefficients of the form are not equal. Take any sequence of positive real numbers and take an infinite sequence of prime numbers and let B be any set of integers. So there exists always, there exists a set of integers, not just a set, but a strictly increasing sequence of integers, which is a phi Sidon set. It's a Sidon set with respect to this rational linear form. And AK minus BK, AK is p-adically close to BK for all the primes PJ with J up to K. So of course, so AK is p-adically close to BK for a large set of primes, and as K gets bigger, AK is p-adically close to BK for a larger and larger finite set of primes. And in particular, if you just let your epsilon k's go to 0, if phi is a linear form with rational coefficients that satisfies this property, and bk is any sequence of integers, there is a strictly increasing phi Sidon set of positive integers a, such that for every prime number p, the set A is p-adically asymptotic to B, in the sense that for fixed p, AK minus BK, the p-adic value, goes to 0 as K goes to infinity. So it's not just that if you have any sequence of integers, you can find a sequence of integers p-adically close to B for some p, but simultaneously for all primes. So that's rather curious. Okay. I want to add, I'm almost done actually, but I want to add just two more remarks. One is just an interesting construction of phi Sidon sets in the case of the integers. So if phi is a linear form with integer coefficients and m is a positive integer, we say that a set B of integers is a phi Sidon set modulo p if whenever phi of B1 up to BH is congruent modulo m to B1 prime up to BH prime, then the two H tuples are the same. The H tuples are equal. So we have the following nice construction. If you take moduli integers m1 up to mr, at least 2 for all I, and if you take r plus 1 sets of integers where the set bi is a phi Sidon set modulo mi for I going up from 1 up to r, so b1 up to b sub r are phi Sidon, are modular phi Sidon sets, and br plus 1 is just an ordinary phi Sidon set, that is a set of integers which is phi Sidon with respect to this linear form phi, then this sum of dilates, b1 m1 times b2, m1 m2 times b3, m1 m2 m3 times b4, and so forth. This is a phi Sidon set, not a modular phi Sidon set, but a real phi Sidon set. So you have a way to blow up phi Sidon sets. And the B's don't have to be distinct, so you can actually easily construct large phi Sidon sets. The second remark has to do with the growth of these phi Sidon sets. Um, so for the classical sit-on sets for the integers, um, so you have a set of integers where a number is a sum of h elements of the set in essentially unique way up to, if n is a1 plus a2 up to a sub h, the only other representation is just some permutation of the a's, but there are no two essentially different representations of the number as a sum of h elements of the set A. Then the standard baby counting argument says that a of x, the growth of the function, the number of elements of the, let's say it's a set of non-negative integers, the number of elements up to x is big O of x to the 1 over h. And there are various constructions of sit-on sets, subsets of the integers from 1 to n, where in fact you can have the right order of magnitude, the number of elements of the set is greater than constant times n to the 1 over h. So there's a really famous and significant result of Erdős that shows the difference between extremal problems of this sort for finite sets and for infinite sets. So on the one hand, Erdős constructed an infinite sit-on set A, where, so these are sit-on sets now in these two examples of where h is equal to 2. So you would expect when h equals 2 that you can't do better than an infinite sit-on set where the counting function a of x is bigger than the square root of x, but maybe you can actually get more than square root of x elements. So Erdős showed that half of that is possible and the other half is not possible. So he constructed an infinite sit-on set A where a of n is basically bigger than some constant times square root of n infinitely often. And in fact, where the lim sup of a of n over root n is at least a half. But he also proved that you can have a of n root n greater than some constant times root n for all n. And in fact, that every sit-on set satisfies this condition that the lim inf of a of n root log n over n is less than some positive constant. In other words, that a of n over the square root of n is less than some constant times 1 over square root of log n for n large. I mean, this is a really interesting phenomenon because you see a sharp difference between the finite problem and the infinite problem. And this comes up in a number of settings in combinatorics. There was recently some very nice paper by a group of combinatorialists, Jacob Fox and others, using exactly this as their model to look at other things in other problems in combinatorics. So we do have an estimate for the size of a sit-on set with respect to a linear form. It's basically just an extension of these sort of most elementary estimates. So you have a field with an absolute value. You take a subset X of the field, its counting function is just the number of elements of the set X with absolute value at most T. So here, unfortunately, T is my parameter and not X, but the counting function X of T is the number of elements of the set X with absolute value at most T in the field. And so we have exactly the bound you would expect, namely, you have a field with an absolute value, you take a linear form with coefficients in the field, let capital C be the sum of the absolute values of these coefficients, and take any subset of the field where phi of x is contained in x. So you take h elements from x, you evaluate phi at the form, and it gives you back an element of x. If A is a phi sit-on subset of x, these are the things we're interested in. Then the counting function is basically x of t, x of this constant c times t to the 1 over h. So this gives you an upper bound for the growth of the phi sit-on set. And in particular, if you take a linear form with integer coefficients and a phi Sidon set, it satisfies this inequality. And one has also the following sort of constructive remark that if you take your linear form with integer coefficients satisfying condition n, there exists a phi Sidon set of distinct positive integers that grows no faster, basically, that a sub k is k to the 2h minus 1 plus k. Okay. All right, so this is some little, I don't know, potpourri of results that come from just trying to extend the concept of a Sidon set to linear forms. I thank you for your attention and happy birthday, Balu. Thank you.
Thank you very much. We thank the speaker. We thank Mel for his nice talk. Are there any questions?
Yes. Sorry, I'm 14 years old, but I mean 13 years too late. But concerning this theorem, A plus twice the second dilate, I mean plus twice A. Yes.
Yes,
A
right.
plus second dilate of A. Yeah. On your first slide, you had something like that.
Yeah. Let me try to find it.
Do you know of anything like that in finite group, Z by NZ? I mean, Knesser's theorem for this kind of stuff. Getting closer.
You mean, sorry, this?
This one, yes.
Yeah.
No, I'm trying to think because this is, as you observe, very old and
Not so old.
well, it's pretty old and
I'm sorry, it's not exactly the topic of your talk today, but
yeah, no, I understand. So you're interested in these theorems about sums of dilates in abelian groups, in finite abelian groups.
yeah.
Yeah. So the answer is I don't know, but it is, you know, I tend to do something and then I go on and I do something else and I completely forget everything that I had ever done. So for example, I noticed when I was thinking about this, that on my computer, I had some titles of something involving linear forms. And I looked and I said, oh, here's this paper, what's in it? And
to tell you the truth, during your talk, I went to MathCnet and went to see whether someone had written something about, I had extended this result. And two people gave another proof of your result, but no one extended it to finite group.
Yeah, so I don't know. I mean, that's a nice question. But you know, there has developed over the last 13 or 14 years a large literature on this subject of sums of dilates, and
Yeah, sure.
which I discovered again exactly as you did. I went back and I looked at MathSciNet and at things that had referenced things and so forth, and you see this multiplicity of papers, and you say, "Oh my God, if I only had a few extra years, I could understand. I could figure out what people have been doing." So, but
Okay, thank you. It's I would like to see it anyway.
yeah. But Boris Buch and I mean, you see Oriel Sarai, I think, and several people have written papers on sums of dilates, and it's a natural question, I think, to ask about this in abelian groups, but or certainly in line MZ, but I don't know.
Maybe I'll send a mail to Oriol.
Yeah.
And ask him. Yeah, sure. Thank you.
Are there any other questions or comments? Mel, what would be an open problem on this topic?
So there's a preprint of this. I have to update it, but there's a preprint of this that I posted on archive a couple of months ago, and it ends with a list of open problems. And certainly they're all still open. And there might be a few more, but it's like, you know, in American politics, at least, there's the following saying, you know, a guy goes to the political boss and says, I need you to do me a favor. I've done a lot for you. I need you to do me a favor. And the boss says, yes, but what have you done for me lately? And so that's the way it is with, at least with my mathematical papers. It's like, I completely forget what's in them as soon as I stop working on them. So I had to go back, and this is only a couple months old, but I've been doing some other stuff. So I had to go back and see what was in it and try to understand it again. And there are some open problems at the end. So the best I can do is refer you to them, because if I try to remember them, I'll state them badly.
Still, thanks for the reply. So if we have young researchers who are interested to try open problem, they can have a look at your archive paper on this subject.
Yeah, most of my papers end with open problems because I can't solve them.
And that's the way to push for progress. Any other questions or comments for Mel?
No, I'm good.
So thank you again.
Thank you.
And we meet again in about 15 minutes. Thank you.
So, Shalom.
Yeah.
I've done better than I did in when we were in India at that meeting last year, when I was trying to give like these Beamer talks. And but it's hard to me to estimate the time. I'm used to talking and having people interrupt. So my talks would normally end after 25 or 30 minutes. So this one made it for 40 minutes. I'm getting a little bit better at judging time.
One is getting used to those tools slowly.
Yeah.
I mean, for this Zoom talk, I essentially double the amount of content I put in one talk.
Yeah,
it's incredible.
Yeah,
it's incredible.
No, because I know when I have, you know, when we have our seminar in New York and I talk, you're actually talking back and forth with people.
Yes.
You know, it's more fun too.
Yeah, on these talks on Zoom, it's I think it's a good thing to really try and go slowly. Otherwise, people get lost pretty quickly. It's a good time. It's a good thing to try to have a slow pace.
Yeah.
No, but if you listen to the talk of Mel, it was not too fast. It was explained enough, but still it goes fast. I mean, we put more content. I don't know. It's really because we don't have the interruptions. I mean,
this is one thing, but there's another thing. When you write on the blackboard, of course, the content develops under your eyes. So, but with these slides, you have the full content on one slide. And yeah, and it's a bit difficult to make the connection between what the speaker says and what is written. So this is why in my talk, I try to have several cuts in a single slide so as to more or less simulate the writing on the blackboard. Yeah, this helps a bit.
So you told me once, Shalom, where is an exposition of Macaulay's theorem?
Oh, there are several.
And you sent me something, but I've forgotten now, and it's probably somewhere on my computer.
Yeah, there is a book by, excuse me. There are several books. Oh, there is a book by Herzog and Hebe. Maybe this is the one I gave you, but there's another one by, oh, I'll send it to you. There are 2 or 3 nice places where there are modern proofs, and one can have an idea of how it's proven and so on. I will send you the. I just don't remember. She's an expert in commutative algebra, and it will come back. And anyway, we'll send you the reference. But otherwise, Herzog-Hebe would be one reference.
And I assume when Macaulay was doing this, the only rings they were looking at were polynomial rings.
Yeah, and their quotients.
Yeah.
Yeah. Oh yeah, sure. She's Irena Peeva, P-E-E-V-A, Irena Peeva, P-E-E-V-A. I forgot the name of the book, but you will find it easily, and it's a very, very clearly written book. Yeah.
Organ is telling me that there's a paper by Alain Plein on sums of dilate and cyclic groups, but of prime order. Prime order is
yeah. So if the size of the set is not too large, then you make a slight gain in the result of Cauchy's development. You make 2 plus some small constant times cardinal T of A.
okay. But you see,
I
would like to apply it to the multiplicative group of Z by NZ. So it's always going to be divisible by 2, and I mean, it's not going to be prime.
yeah.
But well, I'll see whether I can get things out of that. Yeah. Okay. Okay. Okay, this show is stringally with that. If you have a torsion-free group, it works.
Yeah.
But then life is more difficult. Okay.
Is Professor Kumar Murthy joining us?
No, not yet.
Okay.
So let's just wait.
Okay. We still have a few minutes.
Probably somebody can remind him.
We have already informed him today morning, so he
Oh.
knows the timing.
Oh.
No, I think he is in the COVID committee of Canada. So that is taking all his time.
Oh.
And we have correspondence with his secretary as well. So
She can give the talk.
at least there is someone to remind him.
Olivier, have you been collaborating since a long time with Oriol Serra?
No, we worked only. We tried to work only once, and we didn't. I mean, yeah, we didn't manage to do what we wanted to do.
But still, you have a paper, right? Yeah.
Yes. It's with this isoperimetrical method of his and Hamidou. Yes, but you know, I feed problem to people who know additive number theory, and they tell me I need this information. And then I try to get the information, and I tell them, "Can you solve this problem?" And they go. It's back and forth. But then I saw this problem, this result of mail, and it offers very interesting directions. I mean, really.
So for applications in analytic number theory, right?
Yes. Yeah, it's essentially instead
Okay,
of
I will call and check because we still have 3 minutes. I will call and check.
Okay.
Thank you. Yeah.
And Sukumar, you're in Kolkata? Sukumar, are you in Kolkata?
Yeah, I am unmuted now. Can you hear me now?
Yes, I can.
Yeah, I am in
It's
Kolkata.
easier when you're unmuted.
Yeah. One gets stuck now, wherever one is.
Yes. I'll try to come to India in November.
Oh, very good. By that time, things hopefully would be okay.
I mean, it's not worse in India than it is in France. I mean,
Now
Yeah.
most of our students are also away. We are teaching online.
Yeah, I'm online. I'm in the meeting.
ah,
I'm in the meeting, yes.
Okay, he is in the meeting. We can,
great.
Anirbandha, can you please make him co-host?
Fine.
Thank you.
Yes, yes, I'm doing that.
Professor Murthy, can you please share your screen to show
Yeah,
your
probably I
slide?
have to make him co-host, which I'm just doing.
Okay.
Hi, everybody.
Hi.
Can I share the screen now?
Yes, you can share.
Hi, Kumar.
Okay. Hi. Let's see. How do I share? This is it.
So you have a green icon.
Yeah. And then I can make this. I wonder. Let me try to make it full view, full screen, and it'll probably crash. Almost surely it'll crash. Can you see it?
No.
Okay, so what you do now, I stop share and I do the same thing again and it'll work. Stupid computers. Can you see now?
Yes.
Yes, good.
Perfect. So we'll wait 1 more minute before starting, if it's okay. Should we start? Would you be ready? Should we start?
I'm ready. What does Anirban say?
Oh, in fact, so I'm the chairman, so
Okay. So
I'm
then,
ready. That's okay. I think we can start.
Okay.
So it's a great pleasure to welcome Professor Kumar Murthy for the last talk of today's conferences, and he will speak about the least prime in conjugacy class. Please, Professor Murthy, it's yours.
Okay. Thank you for the introduction. Thank you for the invitation. And I know everybody here must be quite tired, so you won't mind if we even finish early. For me, it's noon, so it's in the middle of the day. But for you, I know it's already 9:30, and you've had lots of talks in the program so far. Firstly, let me wish Balu a very happy 70th birthday. I'm sorry we missed the felicitation, but Balu, we wish you all very well and best wishes and many more years of happiness and health and productive mathematical productivity. So very happy to be part of this conference. So I want to talk about this question, which I've been interested in for many years, but I come back to it now and then and think about it. And recently, one of my students, Ren Zhu, wrote his thesis on a particular case of this problem. So I thought it'd be good to present those results. So the issue is this. So I have a Galois extension of number fields, L over K, and let's say the Galois group is G. And you take a conjugacy set, that just means a subset of the group which is stable under conjugation, or another way of saying it is it's a union of conjugacy classes. Then you take a prime of the base field, K, which is unramified in the top field. So it'll factor in some way. And for every prime Q, let's say, in the top field that divides P in the bottom field, you get an element of the Galois group called the Frobenius automorphism. It's simply the unique lift of the map on the extension of residue fields, which raises elements to the power equal to the size of the residue field of P. That gives you an element in the Galois group. And because of this basic relationship, that when you apply a Galois element sigma to a Q, you of course get another prime above P, and the Frobenius just conjugates. Okay, so therefore you get as you vary over the primes that divide P, these things all fit into a conjugacy class, which we call Frobenius sub P, where P is the prime in the lower extension. Okay, so and so this is a conjugacy class. Now let me see if I can, let's see. Yes, okay, good. So then the generalization to the of the prime number theorem in this context is what's called the Chevatoro density theorem, which counts the number of primes of the base field whose norm is less than or equal to x, which are unramified in L and whose Frobenius conjugacy class is contained in this C. Remember, C may not be a conjugacy class, it might be just a conjugacy set, something stable under conjugation. So you count the number of primes where the Frobenius is conjugacy class is contained in this set C, and the Chevatoro density theorem says that it is the Frobenius elements are equidistributed by the discrete measure. So G is a finite group, so it's just distributed by a discrete measure, and so therefore phi sub C of XLK is asymptotic to the size of the conjugacy class divided by the size of the group times the total number of primes of norm less than or equal to x. Okay, so this was known for a long time, but maybe in more recent times, recent being last 50 years, rather than the last 100 years, we have a question has been asked about what is the error term, and moreover, I think it's a kind of modern point of view that the error term has to be effective in all the field constants. So there were various attempts at producing error terms, but sometimes people assumed that certain things were fixed. For example, the base field K is fixed, and so ignored the dependence on the base K, but of course you can't do that. So a totally effective version means it should make explicit the dependence on all of these parameters. So assuming the Riemann hypothesis for the Dedekind zeta function, which is a zeta function of number fields, you get the following kind of error term. You get the main term here as we have here. And then the error term, of course, the x to the half comes from the Riemann hypothesis, that is the zeros of the Dedekind zeta function being on the half line. But then the dependence on the other parameters are like this. There is the size of the conjugacy class that sits here, which is the same as the way it appears here. And then you have a logarithmic term, which is pretty mild. I just will, in general, just write this as script mx. So script m is sort of, in a way, the radical of the discriminant. So this picks up logs of primes dividing the discriminant. And so now, if I have this asymptotic formula, then I can answer the question, when is this positive? Well, when the main, for example, if the main term dominates the error term, then it's positive. So you look at what this is, and let's say you replace this with an x over log x, the size, the conjugacy class cancels out, and then you get you need that x should be bigger than the size of the group squared times log of the script m to the fourth. Okay, that's just from this formula. Okay. But if you can ask a more refined approach, and you can try to improve the here, I'm sorry, the here I had a fourth power of log m, and you can take a more refined approach, and you can in fact prove it with the square of log m. Okay, and now by Minkowski and Hensel, you can replace. Oops, let me see. Now, did I go back? Yeah. By Minkowski and Hensel, you can essentially replace this quantity by log of the discriminant of the top field squared. Yeah, because after all, Minkowski theorem tells you that the discriminant will be bigger than, let's say, for just to understand things easily, k equals q. This will tell you that log of the discriminant is bigger than the size of the Galois group up to a constant. And then similarly, you can get by Hensel, you can get an upper bound involving the primes and the elements of log m. Okay, so basically this is what you get, that x is, as long as x is bigger than some absolute constant times log of the discriminant of the top field squared, there is a prime in this conjugacy class. Okay, so that's a theorem assuming the Riemann hypothesis for Dedekind zeta functions. Unconditionally, there's an estimate like this as long as x is bigger than some sufficiently large power of the discriminant. So here on the Riemann hypothesis, you have the square of the log of the discriminant, and unconditionally, you have a sufficiently large power of the discriminant. This is proved by Legarius, Modlisco, and Montgomery in 1979. And since then, people have thought a little bit about what is the size of this A. See, it's very reminiscent of a Linux conjecture type, Linux constant type of problem. So there's a result of Asif Zaman, who was a student of John Friedlander, proved in 2017 that for sufficiently large discriminants, you could take A to be 35. And then more recently, that was improved to 16. And then the question is, these are sufficiently large discriminants, so someone else has figured out what bound force works for all discriminants, but then it's rather large, 12,577. Question that is, I think it is an interesting question. For example, can you prove A less than 1? That would be a very interesting breakthrough, I think, if you could establish that. Okay. So here's the theorem that I want to speak about today. It's a very particular case. So suppose I have an extension of fields L over K that are unramified. Okay, this is unramified. And suppose it's an SN extension. So it's a non-abelian unramified extension. And I'm going to assume Artin's holomorphic conjecture for the so-called hook characters. So I'll say in a moment a little bit about the representation theory of SN, but there are certain special characters of SN. They're called the hook characters. And we just need to know that the Artin L functions, and I'll say what those are also later on, but they're analytic for those particular characters. And suppose I take the class of an n cycle. So as you know, the conjugacy classes in Sn are determined by the cycle structure of a permutation. So look at the conjugacy class that corresponds to an n cycle. Then you get the following bound. I don't know if this is, if you can see this. I can magnify this better. Yeah. So I get the discriminant of the top field, and then this exponent, and then some power of the log of the discriminant. Okay, let's look at this power. So remember, this is an Sn extension. So the degree of L over K is n factorial. So I'm getting the root discriminant, dl to the 1 over n factorial, and then to a power which is still exponential, but it's exponential in n. Now remember, the degree is n factorial. So this actually is quite small relative to the degree. But in particular, what we get is a bound for the least prime whose Frobenius conjugacy class is an n cycle, which has an exponent of the discriminant going to 0. Remember, I just asked you, let's see if I can go back. Can I go back? Yeah, I just asking you here about, can I get A less than 1? And what I'm saying is that here we've got a bound in this particular case, which actually goes to 0 as n goes to infinity. Now, just to tell you that this is not an empty theorem, the results of Froelich that tell us that there are infinitely many unramified Sn extensions of a given number field. So there do exist such things. Okay, so that's the theorem that I will try to, let's see if we can, we'll try to discuss. Okay. Yeah, okay. So let me make some remarks about this. So first remark is that, well, we're looking at n cycles. We can do it for some other conjugacy classes as well. For example, we can do it for n-1 cycles. We can actually get, here you see there's a hypothesis about this unramified thing. You may wonder why we put that in. That's because if you don't put it in, you get a factor that I didn't like very much, involving the ramification. I think it shouldn't be there, but at the moment it is. So if you don't assume anything about the ramification of L over K, you'll get something with the norm of the different of L over K to the power lambda to the n. And remember, this looks like it's exponential, but the degree is n factorial, so this is still small. Now, in the case that it is unramified, of course, what that means is the discriminant of the top field is simply the discriminant of the bottom field raised to the degree. So it's discriminant of K to the n factorial. So another way of stating the bound that I put in the theorem is that there's a prime as soon as you get beyond the discriminant of the bottom field to the power this constant to the n over n to the 3/2 times the power of log dl. Okay. we can generalize this a little bit more. If the ground field is Q, then then of course there are no unramified extensions of Q, much less an unramified SN extension. But suppose you had an SN extension of Q, which certainly exist, which is unramified over a quadratic extension of Q. In other words, here is Q over L, this one is Sn, and that there is some quadratic field F such that this part is unramified. Such things do exist, they've been constructed. In that case, yes, then you get a similar theorem that is again root discriminant to similar kind of power. And now you actually save something on the bottom of the logarithmic term as well. Okay, again for an L cycle. Now, I just make this comment here again that because the degree is n factorial, this lambda to the n over n to the 3/2 looks exponential, but it's tiny compared to the degree. Okay, so you have something which is, if I want to write it like this, the root discriminant to a power, as small a power as you like of the degree. Okay, and as I said, still it's an interesting problem to try to eliminate this this thing. I would have loved to have a constant here. I don't know yet. We don't know yet how to do that. Okay. Make sure did I? Yes. Okay. Okay. So let's go back and look at the background. Where is this problem kind of coming from? I think there are people in the audience who love the problem, the classical problem of primes in arithmetic progressions, and that's of course the origin of it. So you can consider the classical case where K is Q, and L is the mth cyclotomic field. So then the Galois group is Z mod M star, and this is abelian. So conjugacy classes are singletons, and every conjugacy class therefore corresponds to an element of this Galois group, and the elements of this Galois group are what? If I have an A mod M here, then it's the automorphism that sends the m zeta m to zeta m to the A. That's the and the cyclotomic reciprocity law, which is kind of a tautology, tells you. So what is the reciprocity law? The reciprocity law is the rule by which if I give you a prime P, you tell me what is Frobenius P. Remember, Frobenius P is in general a conjugacy class in the group G. So I give you a prime, and you have to tell me which conjugacy class it is. That will specify a reciprocity law. But in this case, because the group is abelian, I need to tell you an element. Well, which element is it? It's the one that raises, that is A mod M, where P is congruent to A mod M. So the Frobenius is given by the congruence, the residue class of P mod M. Okay? So therefore, asking how often Frobenius P is a given element of the group G is the same thing as asking about primes in arithmetic progressions. So this whole problem of Chebatov is a generalization of the problem of primes in arithmetic progression. So now we've asked what the kind of estimates that we were talking about, the prime of least norm, where Frobenius is a given conjugacy class, is like Linux problem of estimating the least prime in an arithmetic progression. And as you know, there's a beautiful theorem of Linux that says that you only need to go up to a fixed power of the modulus. So if I'm looking for a prime in the arithmetic progression A mod M, I only need to go up to M to some fixed power lambda. And we know a lot about this lambda. For example, Turan observed that if you assume the Riemann hypothesis, anything bigger than 2 will work. So by M squared, you will have gotten all the primes, all the residue classes filled. Now here's something we don't know yet. I don't know even what hypothesis implies it, but Chawla conjectures that 1 plus epsilon should work. In other words, just go past, maybe even m times the small power of log might work, that you should get a prime in every residue class if you go up that high. This is not, as far as I know, this is not a consequence of the Riemann hypothesis. Okay, but now just to compare it with the general kind of theorems we've been talking about before this, if I take this M cyclotomic field, roughly speaking, not exactly, roughly speaking, the discriminant is M to the phi of M. Okay, now you have to worry if, for example, if there are imprimitive characters, you need to take care of that. But in general, sort of morally, if you like, it's like M to the phi of M. So therefore, log of the discriminant is like phi of M log M. And so what Linux is saying is that there's a prime congruent to A mod M, which is as soon as you go to a fixed power of log of the discriminant of this field. Okay, so that should put this into context. Remember what was known? If you, in the general case, we know that if you assume the Riemann hypothesis, you could do it when you go up to log of the discriminant of the field squared. And if you don't assume the Riemann hypothesis, you have to go up to some power of the discriminant. Okay, that's the general theorem about primes in conjugacy classes. And that unconditional bound is nowhere near Linux theorem, nowhere near what Linux proved for the abelian case, but because he proved an absolute bound of log of the discriminant. We can't even get a power of the discriminant less than 1. Okay, some years ago, I made a conjecture about these bounds. It still doesn't get us, it still doesn't quite get us, but it gets us closer to Linux theorem. It doesn't get us this close, but it gets us a little closer, namely as a conjecture still. There are absolute constants A and B, so that there's a prime in the conjugacy class C as long as you go up to this bound, namely the root discriminant to a fixed power times the power of the log discriminant. So before, you remember, we just had a power of the discriminant. That's the theorem. I'm asking whether the intermediate thing before getting here is to prove that you could get a power of the root discriminant. And similarly, if the Riemann hypothesis were true, we got that we need to only go up to the square of the log of the discriminant. But I'm asking whether you actually can do better than that, namely 1 over the size of the conjugacy class times log discriminant. Again, in the abelian case, you won't see this because the sign of the conjugacy class is 1. But in the non-abelian case, you will see this. Okay. So just a remark about why this comment here about the size of the conjugacy class I'm trying to say here, the size of the conjugacy class. Let me just make a comment about that. You see, if you think of, here's the group, let's say this big egg-like structure is the group. And I've partitioned it into conjugacy classes. Here's a tiny conjugacy class of the identity. And generally, if you have a center, any central element will be a conjugacy class by itself. Right? But in general, you'll have other conjugacy classes, and you partition the group. And sometimes you might have big conjugacy classes, and sometimes you might have medium-sized conjugacy classes, sometimes you might have small conjugacy classes. So here, that's a sort of division of the group. Now, I'm taking primes, and if you think of this like a dartboard, I'm throwing each prime at this dartboard. Okay? Then it should make sense that the probability of my hitting a big region should be higher than my probability of hitting a small region, right? And indeed, that's borne out by the Chebotauro density theorem that says there are more primes. The number of primes depends on the size of the conjugacy class as a fraction of the total group. That's true. But in this problem of the least prime in the conjugacy class also, there should be some dependence on the conjugacy class. You shouldn't just get a theorem that says log discriminant to squared or discriminant to an absolute power. There should be some dependence on the conjugacy class, because the heuristic is, if it's a bigger conjugacy class, you'll hit it faster. You know, if you think of you're throwing primes at the dartboard randomly, then you will have a better chance of quickly hitting a large region. Okay, so the bounds should somehow depend on the conjugacy class, and at the moment they don't. That's something to think about. Okay, so and as I said, all of these bounds can be formulated for conjugacy sets and not just conjugacy classes. And so, by the way, sometimes this makes a difference. In some applications, this particular point of view makes a difference. I want to show you one instance where you can actually get exactly what I was asking for. Namely, you can show that the bound gets better as the conjugacy class. So what I did was, some years ago, I took the biggest possible conjugacy set. Namely, just remove the identity element. Okay? G minus the identity element. So what does it mean for a Frobenius element to be trivial? It means that the prime splits completely. That's equivalent to this. So therefore, by removing the identity, and I'm asking Frobenius to land in the C, what I'm looking for primes that don't split completely. Okay. Now, if you ask yourself this question, then a long time ago I showed the following, assuming the Riemann hypothesis, that you get a bound like this: log of the discriminant divided by the order of the group whole squared. Okay, in other words, you can find a prime that doesn't split completely, which is as soon as you go beyond log of the discriminant divided by the group whole squared. So this is stronger than the conjecture I was making before here. If I find it here, you see, I was making the conjecture that it's 1 over the size of the conjugacy class times log discriminant squared. But in the case of not splitting completely, you get the size squared. Okay, the size of the conjugacy class squared. And the idea of the proof of this, which is different from most of the proofs which go about trying to estimate the least prime in a conjugacy class, it compares logarithmic derivatives of two L functions, zeta functions. One is the Dedekind zeta function of the top field, and one is the Dedekind zeta function of the bottom field. And the idea is that if many primes, small primes of k split completely, then this thing is going to look like the degree, the logarithmic derivative of the zeta function of the top field is going to look like the logarithmic derivative of the zeta function of the bottom field times the degree of the extension. Now, small primes dominate the behavior of this thing, especially near s equals 1. And so if you let this pattern continue for too long, you're going to skew the residue at s equals 1. But both of these have a simple pole at s equals 1 with residue 1. So you make that what I just said in words precise, and you'll get this bound. Okay, so that's the idea of the proof of that. So that's the only instance where we have a bound really that depends on the size of the conjugate class, and it's in fact stronger than what I'm conjecturing. Okay. Now, for a general conjugacy class, if you assume not only the Riemann hypothesis, but Artin's holomorphic conjecture, and I'll say a little bit more about that later, then you do get a bound that depends on the size of the conjugate class on the bottom, exactly of the kind I'm saying. Basically, you have some other decorations here, but basically it's this square of the log discriminant divided by the size of the conjugacy class. So we might ask, what more do I need then if I want to get a bound that really depends on the size of the conjugacy class unconditionally? This was assuming Riemann hypothesis and Artin's conjecture. What do I need if I want to do this without the Riemann hypothesis? Maybe I'm still allowing Artin's holomorphic conjecture. What do I need? I need to know the following statements about zero density estimate. So I look at the number of this quantity n sub L sigma t, which is the number of zeros of the Dedekind zeta function, whose real part is between the sigma and 1, and imaginary part is bounded by t. And you know just by the usual analytic number theory argument that this will grow like t log t, and the constant in front is the degree of the top field over 2 pi. So here's the conjecture, also I made in the same paper as the previous conjecture, namely that there's a zero density estimate of this kind, that is the root discriminant times t to the power some some constant lambda times 1 minus sigma. And I'm not sure, but maybe you need to stick in a logarithmic term also, just to be on the safe side. Okay. Although over Q in general, you get estimates that that don't have a logarithmic term, but then you don't have the root discriminant. Okay. So estimates of this kind, as I said, are known. It is this kind of what I'm conjecturing here. If I replace the root discriminant with the discriminant, these things are known. So what I'm asking you really is about the root, being able to use the root discriminant. The other ingredient that we might need to be able to prove these things, just assuming Artin's conjecture, is a statement about zeros near s equals 1, namely that there's there's an absolute constant c, so that in this region of basically width and height, degree over log discriminant, there's at most 1 0, and that 0, if it exists, should be real and simple. Again, we know this. If you don't ask for this degree factor, you know that's easy consequence of the functional equation and the Hadamard product formula. So you know 1 minus constant over log discriminant and mod t less than or equal to constant over log discriminant is known. So I'm asking, can we add the NL? And that again, that's equivalent. Sort of what I'm saying is replacing the discriminant with the root discriminant. Okay, this we don't know yet. But if you had this, then I suspect that you would have most, if not all, the ingredients for proving an unconditional version of an estimate that will involve the size of the conjugacy class. In other words, which will actually get smaller as the conjugacy class gets larger. Okay. Okay. So now let's come to the symmetric group. So symmetric group is, as you know, a set of permutations of 1 to up to n, and you have cycles. So cycles means that I have I1 goes to I2 to IK and then back to I1. And we know that every permutation can be written as a product of cycles. And if you allow the cycles to be disjoint, that's a unique representation. And therefore, you can, for every permutation, you have a unique, this unique product of disjoint cycles. And then you can count the number of 1 cycles, the number of 2 cycles, the number of n cycles. And that gives you a partition of n. So for example, if you have this permutation of on 5 letters, 1, 2, 3, 4, 5, that takes 1 to 2, 2 to 4, 3 to 1, 4 to 3, 5 to 5. That's the product of these 2 cycles, 1, 2, 4, 3, and 5. 5 gets fixed. And that gives the decomposition. 5 is 4 plus 1. Here's a 4 cycle and a 1 cycle. Similarly, if I have this permutation, that gives you this write it as product of disjoint cycles. It's these two transpositions, and still 5 is fixed. So that gives the partition 5 is 2 plus 2 plus 1. You know, 2 cycles and 1 cycle. Okay, so therefore, there's this dictionary between conjugacy classes and partitions of n. So yeah, this point being the cycle structure determines the conjugacy class. In particular, the set of n cycles forms a single conjugacy class. So I have this correspondence with partitions of n, conjugacy classes of the symmetric group, and irreducible representations of the symmetric group. Okay, this last one is just, I mean, for any finite group, I have this correspondence between conjugacy classes and irreducible representations. But let's just make this a little bit more explicit in terms of Young diagram. So if I give a partition P of n, we can look at the associated Young diagram, write the partition as A1, A2 up to AN with the A's in descending order. Then the Young diagram is the one that has m rows. So m is the number of these partitions, elements in the partition. And the ith row will have length AI. So for example, suppose I have the partition 2 plus 2 plus 1 or 5. Then I want 2 rows of length 2 and 1 row of length 1. Okay, this is the Young diagram corresponding to this partition. Okay, so special subset of Young diagram. So you see, I can make a lot of these diagrams, but there's a special kind of Young diagram called a hook diagram. And the hook diagram, because they look like hooks, so they correspond to partitions where there's only a single entry not equal to 1. So for example, you write 5 is 4 plus 1, then here there are 4 blocks, and there's a single 1 block here. If you write 5 as 3 plus 1, there are 3 blocks, and then a 1 and a 1. Similarly, if I write 2 plus 1 plus 1 plus 1, there are 2 here, and then 1, 1, 1. All of these are examples of hooks. So there's only one entry which is not equal to 1, and the others are all 1s. So I told you that partitions and conjugacy classes and irreducible representations are in one-to-one correspondence. So to each partition, there is a canonical module for the Galois group, a canonical representation space for Sn. It's called the spect module. Just write it as Sp. And its dimension can be computed by the so-called hook length formula. So what the hook length formula tells you is, say, for example, let's look at this example of 5, and I have a partition 3 plus 2. So there are 3 blocks and 2 blocks. So for each block, you look at the number of blocks to the right and below. So here there are 3 plus 1, that's 4. Here there is 1 plus 1 plus 1, so that's 3. And here there's only 1, and here there's only 1, and here there's only 1. So I get this numbering. And then it's just n factorial divided by the product of these numbers. So in this case, 5 factorial divided by 12, which is 10. So this This particular Young diagram corresponds to a representation of dimension 10. Okay. So there's a simple formula that, and if I had, let's say, 3 plus 1 plus 1, then as you can see for this one, I have 1, 2, 3, 4, 5, so 5. Here for this one, I just have 2. Here for 1, and here I have 2, and here's 1. So that gives me 5 times 4 is 20. 120 divided by 20, I get 6. So there's a 6-dimensional representation corresponding to this. Okay. So in general, if I have a hook representation, remember a hook representation means I own a partition rather, which means I have only one non-1 element in the partition, and all the other ones are 1. So right, the Young diagram looks like this. So let's say there are A across and B plus 1 at the top. So A plus B is equal to n. Then by the method I just told you about how to compute the dimensions of the representation given the Young diagram, you'll get that it's basically a formula of this kind, n minus 1, choose B. I might be off by plus or minus 1. I usually make a mistake in these things, but it's roughly like this. You get the idea. If you can compute it for yourself. Okay. And moreover, there's one more point that's important. The character of the representation can be computed by the so-called Murnaghan-Nakayama formula. And it's given like this. It's firstly, the interesting thing, the characters of the symmetric group take only the values 0 and plus minus 1. And so, sorry, that's not true. No, that's not quite true. But anyway, they're rational valued, they're integer valued. And what you have is a sum of plus or minus 1s going over certain tableau. But for us, if we're looking at n cycles, this formula, the Murnaghan-Nakayama formula, simplifies to be the following. Namely, if you don't have a hook partition, the value of the character corresponding to, so remember, the partition corresponds to a representation. The representation has a character, namely the trace of the representation. So if that partition is not a hook, then the value of the character on an n cycle is 0. And if it is a hook with R is the unique non-1 entry and the rest are 1s, then the value of the corresponding character on an n cycle is minus 1 to the n minus R. Okay, so these hook representations, the character values are 0 plus minus 1.
What is the sum going over? What's the sum, the T?
Yeah, so you have to, once you've given the Young diagram for P, you have to divide them into certain sub-tableau, sub-diagrams. I don't need to define this rim hook, but a certain kind of hook sub-diagrams of P. So it's obviously there are terms here I don't want to start into. Okay, so but the point, very important point is it's combinatorial. It's completely combinatorial. And also another important point for us is that if I'm looking at an n cycle, the only characters that are not 0 on an n cycle are the hook representations, and they take the value plus minus 1. Okay. Okay. Good. Okay. Now let's look at Art and L functions. So we have, as usual, the L over K group G, and you have a zeta function at the top. It really makes a difference when you can factor the zeta function into L functions, well-defined L functions that behave nicely, because often that means that if you working with these factors, you can prove better theorems than working with the product as a whole. In terms of estimates, what happens is the discriminant, which is the exponential term corresponding to the functional equation of the Dedekind zeta function, gets replaced by some linear combination of ardent conductors, which are the exponential terms corresponding to these LS chi's. So this factorization goes over the irreducible characters of G. And notice, by the way, that each of these L functions appears with a multiplicity chi of 1. Chi of 1 is the degree of chi, the dimension of the representation. Now, the point, of course, is that the reason we have a little bit of a problem in using this factorization, I just said the advantage of having such a factorization. The obstacle is that we don't know the analytic properties of LS chi. We know that it's analytic for real part of S bigger than or equal to 1. It might have a pole at S equals 1 if it's a trivial character. So there's a simple pole if and only if we have a trivial character. Remember, I'm going over irreducible characters. And in general, you have all we know is that we have a meromorphic continuation, but there might be poles. And Artin's holomorphic conjecture is, in fact, there are no other poles, that this is entire apart from a simple pole at S equals 1, which only occurs if chi is a trivial character. Okay. The definition of Artin L functions is generally you don't actually require chi to be an irreducible character to define the L function. And in that case, you would say it's entire apart from a pole at S equals 1 of multiplicity. The multiplicity is the trivial character inside chi, in case chi is not irreducible. Okay, so let's now see if I can give you a rough sketch of how the argument here goes. So just to recall the statement. So I have an unramified extension of number fields. Galois group is Sn. We're assuming Artin's holomorphic conjecture. Something got erased here. I just need it for the hook characters, for the L functions associated to the hook characters. Now you know what those are. And suppose you take the class of an n cycle. Then there are effective constant, absolute and effective constant lambda and mu, so that you can find a prime in the conjugacy class C, as long as you go beyond this power. Okay. So this part of the argument you would go about in a sort of more or less standard way. So we want to detect the primes with Frobenius equal to C. So you just define the indicator function. Theta of P will be 1 if the Frobenius is in C and 0 otherwise. You need to worry about prime powers as well. So you can define the Frobenius associated to prime power to be the mth power of the Frobenius of the prime. And you have to also figure out what to do about ramified primes. And what you do, basically you do an average over inertia. You can still define something here. Okay. So then you can, here you consider the Dirichlet series with this indicator, and then log norm of the prime, norm prime to the minus s, summing over prime powers. So this is basically picking up, apart from ramified primes, this is picking up prime powers whose Frobenius is in C. On the other hand, you can write it as a, because by using orthogonality of characters, you can write it as a log, as a linear combination weighted by the character values at C of logarithmic derivatives of the Artin L functions. Okay. Notice, by the way, that if I want to do this and then I want to use analytic properties of the Artin L function, I only care if for those chi's for which this is not 0. So in the case that eventually we're going to talk about an n cycle, we only care about knowing, that's why we only care about knowing Artin's conjecture for hook L function. Now, we're trying to detect prime in a short interval. So the short interval in this instance is an short interval as short as we can make it at the beginning of the range. In general, you can modify this so that you can detect primes in short intervals at further down range as well. But there are various functions that are better for that than for counting. These are two different problems, right? One is when you want to count the number of primes, that's one kind of problem. And second is you don't want to count them, you just want to detect their presence. That's a different kind of problem. So for the detecting of the presence, as we know already from the proof of Linux theorem itself, it's good to use a kernel function. So these are various kernel functions that have been used. So we're just using these things that exist in the literature. So if you put, therefore, instead of just taking this to get this thing, it is basically a straight logarithmic, a straight integral rather of this function fc of s. But if you weight it with these kernel functions kj, then you will get what we got here. But instead of norm p to the minus s, you'll get some sort of Mellin transform of the functions kj. And the point here, the why that's important is that this inverse Mellon transform. The inverse Mellon transform is compactly supported. That's why these functions were chosen. K2, I'm going to ignore it basically because this function is used mainly to deal with the so-called exceptional zeros. I'm not even going to discuss exceptional zeros now. So, but when you have to deal with that technicality, this is a better function. But in general, we will just use this one. And as I said, its inverse Mellon transform is looks like this, and it's compactly supported. So when we have this sum here, you see it's going to die as soon as norm p to the m is bigger than x to the fourth. Where what is x? X is this parameter that we've introduced. Okay. So you get this, and now, and as I said, we're not doing anything new here. These are the same kernels that Legges, Montgomery, and Lisco used, and many other people have used as well. Okay. So now returning to this formula, we have this contour integral. I mean, this notation means I'm integrating on the line 2, FCFS times KGFS. I get this thing. Now we'll move the line of integration to the left. Remember, what is FCFS? FCFS is this linear combination of logarithmic derivatives of L functions, and in particular, we do have chi equals 1 here as well. So at s equals 1, we're going to pick up a pole, and you see the pole of what is going to give you a term like this: C over G K1 of 1. And K1 of 1, what is it? If you look from here and take the derivative, it's going to be log of x squared, the square of log x. So that's the main. When you take this integral and move it to the left, this term, which is basically what I wrote down here, log np times k1 hat of np, where I'm only going over primes of the Frobenius of C. That is equal to this thing. And now when I move this line of integration to the left, I'll pick up a pole at s equals 1 with this residue. And then I'll pick up a term involving zeros. And then I'll pick up a lot of other terms, partly coming from truncating integrals, partly coming from trivial zeros, or partly coming from prime powers, coming from ramified primes, all the nuisance terms that you have to carry. So that's why I just put an inequality here, that it's bigger than or equal to this, which is coming from the residue of this one, minus the contribution from zeros, and then smaller terms. Smaller terms means you still have to work to show that they are smaller, but they are. Okay. Okay. So then you see that what we really need to do is estimate this quantity here, right? Because this is what we had here, this sum here. That's what we need to estimate, and we hopefully will make it smaller than this. Now notice one important thing. This I said is the square of log x. Okay, so that's where there's an x there, and this sum is also dies at x to the fourth. There's no x really. There's no x here, and so we've got to well, there is in K1, I guess, but you'll see now we're going to get an estimate that basically tells us how small x can be. Okay, so we want to estimate this thing, and we obviously need to only consider the chi's for which chi of C is not 0. And in particular, if C is an n cycle, we only need to consider the hook characters. Okay, now to estimate these sum over zeros, you split it up into two parts, depending on how close they are to s equals 1. So whether they're in the unit circle around 1 or they're outside the unit circle. Okay, so the zeros away from 1 is relatively easy to estimate. So I'm going to just ignore those for now. So basically we have to worry about these zeros close to 1. Okay, here now we need an explicit zero-free region that I proved some years ago. So this is sort of the generalization of the old Landau type zero-free region for abelian L functions. So it's 1 minus constant over the degree cubed, the degree of the character cubed, times log of the Artin conductor plus the degree of the base field times log t plus 2. Right? In the abelian case, of course, chi of 1 is 1, so this disappears, and chi is like log of your modulus. And so this looks like the usual 1 minus constant over log q t plus 2 to 1, that kind of thing. And I allow one possible exceptional 0 if the character is abelian. Okay, so this is a theorem we proved some years ago. And so using this, you get an estimate for this K1 at zeros. And after you put this together, you'll get a sum like this, chi of 1 to the 7th times log of the Artin conductor squared. Okay. The x now here, notice, plays no role. And so now if I put this back into the sum over the irreducible characters, notice I've excluded this. Remember here, I said it's possible there's an exceptional 0. I'm ignoring the exceptional 0 for a moment. It says consider the case where there is no exceptional 0. So I'm summing over non-exceptional zeros here, and I have this kind of bound. Okay. So now if I just partition this, yeah. If I partition this, I want to keep chi of 1 with log a chi, and then keep the remainder chi of 1 to the 5th, excuse me, 5th here. Let me see, did I do this correctly? I had a 7, yeah. So I take chi of 1 squared. Sorry, I'll write this as chi of 1 to the 5th times chi of 1 squared. So the chi of 1 to the 5th, just keep it here, and then the chi of 1 squared log a chi squared is less than or equal to this whole sum of this whole thing squared. This is a really crude estimate. So therefore what we need is, if we want the bound to be non-trivial, we need x to be such that log x squared is bigger than this quantity here. The dot 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 means there are other terms that are quite nuisance actually, that require a bit of work, but they're not that interesting. So once again, only the hook characters contribute to the sum, and we know that for each r between 1 and n, you have a hook character, which corresponds to this partition and has roughly this degree, and the value of the character is less than or equal to 1. So this is, you can just replace it by 1, and this is a big deal, you see, because if you look at the usual estimates, the only way general estimate you have for chi of c is chi of 1. And that jacks up these estimates, these powers here, so that's bad. But here, it's being bounded by 1 is a big saving. So anyway, you get n minus 1 or choose r to the 5th times this chi of 1 log a chi squared. Okay, and now there's a simple combinatorial formula that if I take the kth powers of the binomial coefficients, it grows roughly like this. So in particular, the 5th power, I will get it bounded by 2 to the 5n over n squared. And now there's this log a chi, this Artin conductor that we have here, that grows like chi of 1, the degree times the degree of the base field times some stuff coming from ramified primes. And so this chi of 1 log a chi, again, if for a moment, if you ignore the nk, it's roughly this n minus 1 or 2 r squared. So you get 2 to the 2n over root n. And putting all this together, you get that you need log x squared to be bigger than 2 to the 9n over n cubed. So that gives you a bound on x. Now, if I were to, you get a bound like this. Now I've omitted lots of details here. Firstly, remember we said here that there's the zeros near 1 and the zeros bigger than or equal to 1. Yeah, it's generally true. These are not that problematic, so we can handle that. But then the next thing is, what do you do about the exceptional 0? That is rather problematic. You need to develop a version of the Doering-Heilbronn phenomena, and you need one which assuming Artin's conjecture, you can get such a bound, which depends on the Artin conductor, and that's a bit of work, but so that has to be done. And then the last thing is ramified primes and prime powers, which is not so hard to do. But there are quite a bit of details once you get that in order, then bound works. I think the point is that the SN extensions deserve greater attention from the Chevatarov point of view, because they have the representation theory is so explicit. You know quite a bit about it, and I wondered if we could approach these general conjectures from this point of view for Sn. Also, the issue of this exceptional zero when it occurs is that we know that for certain classes of groups, yes, there can be an exceptional zero, but if you look at them in some kind of family, they don't propagate. They don't propagate propagate so easily. And so if you're looking at Chebotauro not for just one field, but some family of fields, then it's possible this problem, the exceptional zero, at least in the case of Sn, might simply disappear, which is a very important thing if it happens. So I just leave you with this thought that Sn extensions deserve greater attention from the Chebotauro point. Thank you for your attention. Once again, Balu, happy birthday, warm best wishes, lots of happiness and mathematical productivity in years to come. Thank you.
Well, thank you for this wonderful talk. Are there any questions, Paul?
I have a question.
Go ahead.
Oh, okay.
Who are you?
So,
who are you? Can you identify yourself?
yes. Sorry for coming in late. I was actually teaching a class and I just got so sorry about that. So slide 24. Can you go to slide 24?
Slide 24. Yeah.
Yeah. So right there, is it if you were to use Cauchy-Schwarz on the character part, don't you get a saving of don't you get order of the group divided by the size of the class at the very top line? The very top line, that's right there.
Yeah.
If you use Cauchy-Schwarz, don't you get summation chi of c mod squared over all the characters, and doesn't that give you a saving? Doesn't that give you something like mod g over mod c or something like that?
But the problem is here you get much better, because if you see, the only characters you need to worry about are the hook characters.
Yeah, why is that? Why are you only
because this formula, this one, that tells you that if I have any partition, okay, the corresponding character on an n cycle is 0 unless you have a hook character.
I see. That's the punchline. Okay,
and
I missed that. Okay.
And on top of that, on hook characters, it's only plus minus 1.
Yeah. Okay.
And there are only n hook characters. Instead of worrying about like you have a group of order n factorial.
Yeah.
You only have n characters. It's tiny, really tiny.
Mm-hmm.
So that's why we focused on n cycles, because we could do it.
I see. So if you focus on n cycles, only the hook characters come into play, and then you have an explicit formula for these values, and so you exploit all that.
Exactly. So it's a big deal to say that this chi of c is just plus minus 1, instead of saying, we've had this problem before, when you try to estimate that what can you do? Yes, you could try to do Cauchy-Schwarz. You can put chi of 1, just becomes too big. And here that doesn't become a problem. And so some of this will work for n-1 cycles too. Ren worked this out in his thesis. You get n-1 cycles as well. And now the question, of course, actually, I think if you were to start imposing like the cycle structure, then you will get some bounds in terms of the number of cycles of different lengths. And so you can vary over all those and see if you get you'll get some bounds.
Very nice. Okay. Thank you. Yeah.
So, are there any other questions?
Okay, I have a quick question. How about, are there other groups besides this symmetric group where you have such simple structure? Some subgroups, I guess they don't contain they're not an AN, I guess. There should be some subgroups, like, do you know others?
We haven't tried. I've not looked so carefully at them. I don't know. I bet there must be. I mean, so far, I don't know people who've looked at it from this point of view, so there might be. I don't know.
Okay.
Yeah.
Thanks.
You're right. If you take AN, it's much more complicated.
Right. Oh yeah. Yeah. AN is the worst case in some ways, and SN is really good. Yes.
Right. And as I said, there's another thing about exceptional zeros not propagating. In SN families of SN fields. So if we develop what we mean by that, then we should see some other improvements as well.
Right. Okay. Thanks.
Other questions, comments, remarks?
You're done? Everyone can go to sleep now. Because
So if not, we thank you again. We thank the speaker again.
Thank you.
So I would like to thank Professor Shalom for chairing the session and all the speakers of today. Thank you.
Thank you.
So we meet tomorrow afternoon at 1 o'clock Indian time.
Hey, Dinakar, are you around?
Yes. Hello.
I haven't chatted with you in a while.
Yeah, but here everybody can hear us, including Ram. Yeah. Okay. Yes. Yeah, we should.
We
Yeah.
should connect. Yeah. Good. Okay.
All right.
I'll see you.
See you. Yeah.
Bye.